Okay, so today we will once again recapitulate some of the essential ideas in the study of quantum mechanical correlation and go over single photon interference again. But then we will come back to this topic a little later. So once we recapitulate the stuff that we did last time, I would like to try to switch gears and discuss the concept of a beam splitter. So how a beam splitter works and what are the transformations involved, so on and so forth. So today we will do classical beam splitter, and next week we'll study the quantum mechanics of beam splitter. Okay. And then once we are done with some of these things, some of these concepts, we once again get back to single photon interference, two photon interference. Okay, so now last time we calculated the probability that a field makes a transition from some initial state I to some final state F, and what it is. And this is pretty much that's what it is. Now, of course, this assumes this expression assumes that the state is pure. If the state is mixed, the same quantity, the probability of absorption. That's what it is. And we saw what E minus and E plus. So they are basically the quantum analogs of complex analytic signal. Divided. So that's what it is. And T divided of R omega is same as T of R minus omega. Okay. So now let us look at once again briefly recapitulate what we discussed last time on single photon interference. And of course, the correlation function. So this is what it is. So this is the correlation. This tells us how the field, the quantized field operator at R1 T1 is correlated to the field at R2T2, the quantized field operator at R2T2. Okay, so this tells us how the quantized electric field is correlated at two different space-time points. Right. So the next thing is interference within the quantum description. So we looked at this problem using Michelson's interferometer. This one is Michelson's interferometer. So look, what we have is so the source produces one photon at a time. Okay, so unlike the graphical setting where the source produces a fairly strong beam, a beam with high intensity, in this case we have a single photon source. So the source produces one photon at a time, and the photon is indestructible. So you can't split the photon into two halves. So either the photon will get transmitted, either will take this route pathway or this pathway. Okay. So basically this is pathway one. Pathway two. Right. So either the photon will get reflected at the beam splitter, hit this mirror, and then pass through this beam splitter again on its back pass and reach the detector, or it will get transmitted to the beam splitter, hit this mirror, get reflected here, once again get reflected at the beam splitter, and reach the detector. So the photon has two possible alternatives to choose. In order to get detected, right? So by single photon interference, what we mean is it is the interference between the two pathways, two alternatives. So in quantum mechanics, you always assign a probability amplitude for each pathway, for each alternative. So it is interference between two alternatives. So we saw that the photoelectric field at the detector. So let us say the detector is located at the location R, whose coordinate is given by vector R, and you measure, you detect the photon at time t. So, and let us say that the photon takes time t1 to reach detector through pathway 1 and time t2 to reach the detector through pathway 2. Okay. So there. That's what it is. So this is not mathematically, this is very similar to what we have seen earlier when we studied temporal coherence in the classical setting. Now, the comparative detection that's what it is. Now, when we worked out the math and we got what it is. So this is what the terms stand for. Okay. Now you can clearly see a parallel between this one and what we saw in the classical setting. So the classical setting, I don't have, I will write it here. Here we see a parallel. Mathematically, these two look identical, but the interpretation is very different. So here, in the practical case, the intensity gets distributed between the two arms of the interferometer. However, in the single photon case, the photon is indestructible. So there's no way the photon gets distributed between two pathways. So it can, every time you shoot a photon, it can take either of the two pathways. So in the quantum mechanical case, the single photon interference means the interference between the two possible alternatives. And when you do the math, this is what you get. Fine. So this is what it is. So this is the graphical interference. Quantum. So that's what it is. So one thing is, of course, we cannot arbitrarily change the lengths of the two arms, because if the difference in the path length exceeds the coherence length, or if T2 minus T1 exceeds the coherence time of the source, then the pathways become distinguishable and you will no longer observe interference. So, even to observe single photon interference, it's important to ensure that the difference in the path length is within the coherence length, or T2 minus T1 is less than the coherence time tau sub c.
Excuse me, sir. One doubt.
Yeah, please.
Yeah, in a classical sense, previously you were saying about this coherence length and the interference pattern will not be so clear. Contrast will not be there.
Right. No, but yes. So if you exceed the coherence length, even in the the interference will vanish. The fringes will disappear.
In this case, how to check whether how the pattern will be visible? Because already it seems like a single photon. Like how to see an interference pattern in this scenario?
Oh, so what happens is, it's not that, so you shoot one photon at a time. So it's not that you just use one photon, you have a source that produces one photon at a time. Okay, so the first photon is ejected from the source. Now it has two alternatives, right? It can either take pathway 1 or pathway 2, and it will reach the detector, right? Now, the second photon, then the second photon emerges from the source. Once again, it has two alternatives. Okay? Now, it will reach the detector. Now, you do this experiment for a collection of single photons. When you do that, you will observe the interference pattern. In fact, this experiment was done in the 1980s. There are many ways to realize this one. So, one of the labs in Japan did an experiment in 1980 where they had a source. Maybe they did this with electrons. So they had the source that produces single electron, so one electron at a time. Okay, and now they just put a photographic plate, and the room was, all the lights were turned off, so that you don't get to observe the electron or get any path information. So they wanted to make sure that the no path, the concept of indistinguishability is enforced in the setting. Okay. Now, the electron will take one of the two alternatives. In that case, they built an N double slit setup, and then it will be captured by the photographic plate. So, when after a few days, they observe that the electrons on the photographic plate form the interference pattern. So the electrons then strike the photographic plate at random form. They form a definite interference pattern. Okay. So in this case, in this setup, in Michelson interferometer, what you will do is you basically send one photon at a time, and then you detect it. Now, when you do this experiment for a collection of single photons, you will observe the interference pattern.
Still, one doubt what I'm having is either of the two path, if it takes, only one detector is there. In that detector only it will be sensed.
Yeah, so in this case, both paths so no matter which pathway the electron takes, you just need one detector to detect the photon, right? I mean, in this case, they're dealing with photon. I'm sorry, my apologies, not electron. Yeah. So, but yeah, only one detector is more than sufficient.
So now, generally interference in the sense, at least two things will collide or something. I am not able to visualize in this. Only one photon is coming out of the two path. It took some one path, and then it finally reaches the same destination. So what pattern will be able to observe? I am not able to visualize.
So this is not an interference between two fields. Okay, this interference is a bit abstract. So this interference is between the two alternatives. It can take either pathway 1 or pathway 2. So look at it this way. So this is the Young's double slit setup, right? Now you have two slits, S1, S2. So when you shoot a photon or an electron, it can either go through S1 or S2. Now the photon will not simultaneously go through S1 and S2. So basically, this microscope interferometer is a variation of Young's double slit setup. Instead of slits, you have two alternatives, two pathways. So either the photon takes pathway 1 to reach detector or pathway 2 to reach detector. The fact that you have only one detector is perfectly fine. Because what this interfering is the probability amplitudes for both these pathways interfere.
So from the detected signal, how can we differentiate between path 1 and path 2?
No, you should not. That's the whole thing. If you can distinguish between path 1 and pathway 1 and pathway 2, there is no interference. Then the two paths become distinguishable. Right? So, if you recall Feynman's thought experiment, the thought experiment says that as long as you don't observe the path of a photon, you observe the interference. The moment you try to get any information about the path that the photon took, the interference vanishes. Then it no longer behaves like a wave, it behaves like a particle. So here you don't want to know which path the photon has taken. That's very crucial to observe interference.
Yeah, this thing you told earlier, which I remember, but yet after doing this, what is the thing which I'm understanding or taking away? I'm not able to get.
So what is it? No, you measure the photon. So all these things, the probability of detection can be related to so this is nothing but, so if you look at the structure, now you can see that this corresponds to, mathematically this corresponds to what you observe in the classical case, correct? So this,
yes.
This is the second term, K1, K2 star times this one is the complex conjugate of the first one. So this dotted box is the interference term. Now, what it means is when you detect one photon at a time and plot its distribution, then you will observe an interference pattern. That is what is happening here.
Okay, roughly how the pattern will be? Like,
oh, you mean how the pattern is going to be? So it's very similar to what you observe in the Young's double slit setting. In Young's double slit setting.
In this also.
Yeah, so the notion of interference is the same, right? From an experimental standpoint, interference means you should observe bright fringes and dark fringes, correct? There should be bright and dark spots.
Okay. So we are just shooting single photons, yet the pattern final thing will be similar, but which path it took will not be able to observe.
You should not, if you can,
Yeah, understood.
observe. If you, there are ways to observe. If you try to observe, you won't observe interference.
Okay.
So, okay. So basically, you arbitrarily increase the length of one arm of your interferometer such that you go beyond the coherence length. Okay. Then the path becomes pretty much distinguishable because based on the time of detection, you can pretty much say which path the photon might have taken, right? Because one arm is much longer, significantly longer than the other. In which case you lose the coherence, and you also you're able to extract the path information, the interference vanishes. You will still be able to detect the photon, but you won't, from that you won't be able to observe any interference pattern.
Okay. Thank you.
Yeah, so it's not as if you always capture the photon. So here's the thing. Single photon interference is a manifestation of the wave nature of a photon, right? And you observe that when you erase the path information, when you make the two paths indistinguishable or identical, when you are able to extract any information about the path, you don't destroy the photon. It's just that you will detect the photon like you detect a particle. So in that case, the particle nature manifests. So that's what it is.
Okay, sir.
So, but we will come back to this one a little later. Once again, so this is not the final discussion on single photon interference. We will come back to this in a few weeks' time. We will once again, following this, we will discuss two photon interference. So we will discuss quite a few novel quantum phenomena. But this is just, in some sense, a trailer. Like, what are the kind of phenomena, what kind of problems we hope to discuss in quantum optics? If you, so one more thing. So if you know, so let us say that amplitude, the probability amplitude for pathway 1 is psi 1. For pathway 2 is psi 2. Now, if you know which path the photon has taken, then in this voltage, mod psi square is basically mod psi 1 square plus mod psi 2. Right? Now, if you don't know which path the photon has taken, then it's pretty much this one. You have to add the amplitude before you calculate the mod square. I'm just simplifying this one. This is the interference term. Why? Because it can be written as, you can write these complex quantities in terms of their modulus and phase. Now, do you see this? This is how you get the interference term. When you arrange the path information. But this is just a simple description, ignoring all the complications. Okay, so how about this one? Whatever so the kind of correlation that we have looked into until now is the 2-point correlation. But can we discuss higher order correlations like 4-point correlation, so on and so forth? The answer is yes. Or 2 photons. So we will discuss how to produce 2-photon fields a little later, but let us assume that we have 2 photons and we have 2 separate detectors. So the question that we wish to answer is, one photon is observed R1 D1. So this is the question that we need to answer. So of course today we will just write down the formula, the way we will be computing these the joint probability. Then, so for a Q state, once again we'll start with Q state. But this corresponds to the joint probability density of detecting one photon at R1 T1, the other one at R2 T2. So this is given back. We play the same game that we played for the single photon case. complex conjugate. Yeah, this complex conjugate will flip the order. So this is what the final state manifold forms a complete set. So we have so this one. The name for this coincidence probability. Why is it called coincidence? Because there is a probability of detecting two photons at two different space-time points. So you detect a one photon at R1 T1 and another photon at R2 T2. So this is a joint detection of two photons at two different space-time points. So that's why it's called coincidence probability. Now, of course, we just worked out the simple calculation for a fused state, but you can pretty much calculate this one if the state is mixed as well. So in that case, go to the density operator, and this is how we calculate the joint probability. So, can we then study the correlations at various space-time points? The answer is yes. So, in order to calculate, say you have four space-time points. What is this? formally, this is the expression. What does it tell us? We have four space-time points: R1, T1, R2, T2, R3, T3, and R4, T4. What are we calculating? This tells us, this calculation, G2 of this R1, T1, R2, T2, R3, T3, and R4, T4, this quantity tells us how photon 1, how the quantized electric field corresponding to photon 1 is correlated at R1, T1, and R2 and R3 T3. Likewise, how for the second photon, how the field is correlated at these two space-time points, R2 T2 and R4 T4. Okay? So basically, we are calculating the joint correlation of the two photons at two pairs of space-time points. Okay? Any questions? So this is important. So basically, this just tells us that how photon 1, how the field corresponding to photon 1 at R1 T1 is correlated to the field at R3 T3. Likewise, how the field, the quantum electric field of photon 2 at R2 T2 is correlated to the field at R4 T4. This is important. So I want to pause for a moment because before we start the discussion on beam splitter, I just want to pause for a moment and are there questions on this because this is important to appreciate. So I have the notion of coincidence probability and multi-point correlation functions are clear. I said I want to pause for a moment before we start our discussion on beam splitter. I want to make sure that these ideas make sense to you. So, I asked whether the notion of coincidence probability and the notion of multi-point correlation function are they clear? So,
Yeah, we can see that till coincidence for the 2 points, it's been extended for the 4 things also, right?
Yes, but 4 things.
Like 4 points and 4 instants of time.
That is true. We have 4 instants of time, but you have 2 photons. So this is for the case of 2 photons. So this G2 of R1 T1, R2 T2, R3 T3, and R4 T4 tells you how photon 1, how the field, the quantized electric field corresponding to photon 1 at R1 T1 is correlated to the field at R3 T3. Likewise, for photon 2, how the field at R2 T2 is correlated to the field at R4 T4. So basically, you're studying the joint correlation of 2 photons at 2 pairs of space-time points. So that's what this 4-point correlation tells us.
Okay, so the initial thing was that photon 1 was at R1 T1 and photon 2 was at R2 T2.
No.
No. The why it is told like photon 1 from R1 to R3 alone?
Because so in the earlier case, G1 for single photon case, or maybe I should erase this and write somewhere else. Right? So this is something that we have seen. So in the case of single photon, this tells us how the field at R1 T1 is correlated to the field at R2 T2. We just have one photon.
Yeah, that's okay.
One electric, one quantized electric field that corresponds to that photon. Correct? So here we have two photons. Right? So you have two quantized electric field operators to describe the two photons. So you're trying to calculate the correlation of the two photons at two pairs of space-time points. One for photon 1, the other one for photon 2. But the joint, basically it's a joint correlation. It's not as if you treat the two photons as two single photons.
Okay, but yet the marking like the arrow mark what you made, photon 1 between 1 and 3 and 2 and 4.
So
Like,
yeah, true. But so that is the simplified case. But so maybe I'll remove this one because you can also have the case where the photons are entangled. We'll come to that later.
Okay.
So right now you can just, if it confuses you can just see this as the correlation of two photons at four space-time points. And this is how you calculate the joint probability of detection. So this is the coincidence probability, the probability of detecting a photon at R1 T1 and another photon at R2 T2. Okay, this one.
Okay, sir.
So that's what it is. Okay, so we'll start our discussion on classical beam filters. So what is this? So as the name suggests, beam filter is just a beam. It's a device, passive device that splits the incoming beam into two portions. Let us say E1 and E2. Input ports or input beams, incoming beams. E3, E4 are the outgoing beams. they correspond to the output codes. For simplicity, we assume that all the beams have the same polarization, frequency, so on and so forth, and we are going to ignore losses. So, our goal relate the input fields to the output fields. So what do we mean by that? How are E1, E2 related to E3, E4? In other words, can we express E3 and E4, the outgoing fields, in terms of E1 and E2? Okay. And let us assume that the beam splitter has a transmission coefficient T and reflection coefficient R. So in general, these will be complex coefficients. Such that mod T square is 1. Or we can show that mod T square plus R square will have to be 1. Okay, so how do we express E3 in terms of E1 and E2? Look at E3 here. E1 gets transmitted and reaches output port 3, and E2, the reflected portion of E2, will reach output port 3. So that means E3 is PE1 plus RE2. Likewise, you look at E4. The transmitted part of E2 reaches output port 4, and the reflected part of E1 reaches output port 4. So that is this is the input output relation. So one important condition that the system should satisfy is the conservation of energy. So what is the total energy of the two incoming fields? And that should be equal to so E1, E2, E3, E4 correspond to the fields. The fields that are injected into the beam splitter and the fields that emerge from the beam splitter. Okay. So this is the conservation of energy. So we won't have time to complete a discussion on the capital base blood, so we will sketch the idea and continue this next week. But for the next few minutes, we will proceed further and see what we get. We'll just work out the algebra a little bit. So E3 is T. Now take the complex conjugate. E star, E1 star, E2 star, right? Likewise, E4. E2 star. So now we can calculate mod E3 square and mod E4 square. Which is so we get plus so the fourth term is basically the complex conjugate of the third term. So this is what we get. This is mod E3 square. So mod E4 square is E4 conjugate E4. Or even plus TE2. And then we have so that's what we have here. Right. So what does the principal conservation value tell us? Mod E3 square plus mod E4 square should equal mod E1 square plus mod E2 square. So that is so this is mod E3 square, and now write down the result for mod E4 square explicitly. So let us plot the terms. So mod, yeah, mod t square, mod e1 square. Likewise, yeah, e2 square plus your e1 star e2. Plus the, now these two. So this should be equal to, yeah, that follows from the conservation of energy. So what does it mean? We have mod e1 squared on the right hand side. We have these coefficients which multiply mod e1 squared. So this tells us should be 1. Okay, and likewise, these terms, the coefficients of e1 star e2 and e1 e2 star should vanish because otherwise energy won't be conserved. Okay. So these two are very important. Now, the fact that whenever you consider a beam splitter, you always, the sum of the square of the transmission coefficient and the reflection coefficient, if they are real and if they are complex, the sum of the mod square of T and R should be 1 because that follows from the conservation of energy. If it is not 1, if mod T squared plus mod R square is not 1, it means that the beam splitter is not lossless. So energy is not conserved, there is some dissipation, that's what it means. But here we are assuming the ideal case where the beam splitter is lossless. Right. So we have arrived at these two conditions. So we will use them and then try to relate the incoming field to the outgoing field. We'll relate the outgoing fields to the incoming fields, and then we will consider various cases. So what if the beam splitter is 50-50? Say 50-50, the transmission coefficient equals the reflection coefficient. So what kind of relationship we get? And then we'll go to the quantum mechanical version of the beam splitter. So how do we discuss the quantum mechanical beam splitter? So what I mean by that is, instead of classical fields, we have quantum states of light, like single photons impinging upon the beam splitter. How will the incoming modes be related to the outgoing modes in terms of operators and what kind of commutation relations we need to satisfy? So that's what we'll discuss next time on Tuesday. Okay. The next class will be on Tuesday, coming Tuesday.
Okay, sir.
Any questions on the classical beam splitter, whatever we discussed so far? Any questions on the algebra?
No, sir.
Okay, we'll make coming Tuesday. Thank you.